Hello everyone, welcome back to my channel Be an Architect. In the previous videos of this Memory in iOS series, we have explored concepts like stack versus heap, ARC, retain cycle, and copy on write. Today, we are going to answer another important question: escaping versus non-escaping closures. Most developers know that at escaping means the closure executes later, but that isn't the interesting part. The real question is, what changes in memory when a closure becomes escaping? Let's answer that by the first understanding what happens when any normal function executes. Let's start with the simple example. When main starts executing, Swift creates a stack frame for it. Now, inside main, we calculate sum. Immediately, another stack frame is pushed on top of the existing one. Let me show you visually. Inside this stack frame, Swift stores parameter A, parameter B, and local variable result. All of these are temporary values that exist only while calculate sum is executing. The moment the function reaches return, its work is complete and Swift removes the entire stack frame. The parameter disappear, the local variable disappear, the temporary memory is reclaimed immediately, and notice something important here. The heap wasn't involved at all. This is the default memory behavior of every normal function. Now let's take another example. Now I'm introducing a closure. Notice that transform is not marked with at escaping. That means it's a non-escaping closure. Swift guarantees that this closure will execute completely before fetch local data returns. Let's see what happens. The function starts, the stack frame is created, the local variable cache is created. Now closure executes immediately using cache. Once the closure finishes, execution continues normally. Finally, the function returns. At this point, the closure and the function shares exactly the same lifetime. Neither of them survives after the function returns. From a memory perspective, there is no long-lived ownership. Nothing needs to stay alive after the function completes. This is why non-escaping closures are Swift's default behavior. Now, let's make one small change. Instead of executing the closure immediately, we are storing it. Ignore the errors for now. Notice the at escaping keyword. This changes everything. The function starts, the stack frame is created, but instead of executing the closure, we store it into stored closure. Now function finishes and the stack frame is removed. Let me show. But the closure is still available. Why? Because something else now owns it. The function no longer owns the closure, stored closure owns it. Since the closure needs to outlive the function, Swift creates heap managed storage for it. This is the key behind at escaping. It isn't about syntax, it's about extending the lifetime of memory beyond the lifetime of the function. Now, let's take a real-time example. This is exactly how URLSession works. Fetch data starts, it creates the network request, it passes the closure to the URL session. The network request begins, then fetch data immediately returns. Its stack frame is removed, but the network request is still running. So, who owns the closure now? Not the function. The owner is URLSession task. The task retains the closure until the server responds. Only after the response arrives does the task execute the closure. Once the callback finishes, the task releases it. ARC sees that no strong reference remains. The closure is deallocated automatically. Now let's take another example. It's a view model where a completion is called, and within the completion scope we are calling self.loadData. Because escaping closures live beyond the current function, they can also capture objects. In this example, the closure captures self. Now the view model owns the closure owns the view model, neither object can be released. This creates a retain cycle, and the fix is straightforward. Simply define self as weak, and that's it. A weak reference says, I need access to this object, but I don't want to own its lifetime, and that's it. Now, let's summarize everything. A normal function stores its temporary memory in the stack. A non-escaping closure shares the same lifetime as its function. An escaping closure needs to survive after the function returns. So Swift creates heap managed storage for it and lets ARC manage its lifetime. That's why at escaping exists. It isn't just a language keyword. It's Swift way of saying the closure's lifetime is no longer tied to the current function. If this video helped you understand the memory story behind escaping closures, let me know in the comments. In the next part of this series, we will explore how closure captures object and how retain cycles happen internally. Thanks for watching, and I'll see you in the next video.